Hey guys, it is time for the lesson on rational functions, graphing rationals. Okay, depending how the meet scheduling goes, I think I previewed this for you before you watch this video, but either way, rational functions are functions where you have a polynomial over a polynomial, and you therefore have some undefined places. There will be holes in some of the graphs, okay? And there will be both horizontal and vertical asymptotes. Make sure you know the difference between those words. All right, you do not have this slide in your notes. It says a rational function is the quotient of two polynomial functions, okay? The domain is the set of all real numbers except those, excluding those, okay, that make the denominator 0. So excluding values that make the denominator 0. One of the simplest rational functions is just 1 over x, okay, which would look like this over here. It has asymptotes of vertically the x-axis and horizontally the y-axis, okay? And you can do transformations on that. Does it not have any more pictures here? Okay, so just real quick, you could put, this would slide to the right 3 and up 5, so it would make the y equals horizontal asymptote at 5, because right now it's y equals 0, or the x-axis, and it would make a vertical asymptote at 3, which slide that vertical asymptote to the right 3. So the graph would be over here, and up 5, pretend I'm counting by 2s, okay? So that's 5, and it would be here and here. All right, so I'm going to talk about that one, because most of the ones we're going to do are be more complicated than that. Graphs of rational functions have asymptotes. Now you need to remember that those are lines that the graph stays very close to eventually, okay? If you have a vertical asymptote like these going up and down, their equation will be x equals some number, and the graph will never touch or cross those, okay? Vertical asymptotes are never crossed. They're not even touched. But horizontal asymptotes can be crossed. We will do one where the graph crosses the asymptote and then stays just below it. It's kind of weird, but horizontal asymptotes, which are y equals lines, y equals 2, y equals 0, whatever, those can be crossed, okay? But the asymptote, or the function, stays near that. All right, I don't think you have this slide either. I don't think we really need to talk about this. I think I already did. Vertical asymptote is x equals 0. Horizontal asymptote is y equals 0. All right. Now, when you take a function, a rational function, you're putting a polynomial over another polynomial. If those have no common factors, okay, then these are the steps we're going to go through. If they have a factor in common, then there's a hole, and that's going to be on the back of the notes in just a minute. So you would look for vertical asymptotes, and those will occur wherever the denominator equals 0, because those are places that it cannot go. So if you do the domain, you say the denominator cannot equal 0, and then instead it will have a vertical asymptote at whatever that is, x equals. So if you had this, you would say the domain is all real numbers except x cannot equal -2. And the asymptote is actually x equals -2. The thing is, a vertical asymptote is a boundary line. It's not actually part of the graph. The graph never hits that line. So we talk about it and ask you to define it, but it's not actually part of the graph. It's a boundary. All right, horizontal asymptotes occur, or 3 different ways we can look at this. when you have a function on the top or the bottom that is, so the function on the top is less degree than the bottom. So you have an x squared minus 4 over an x cubed plus 6x minus 2, okay? This is degree 2 over degree 3. Therefore, it's bottom heavy, or the top has lesser degree than the bottom, and it will always approach y equals 0. That's because if you put a really big number in there, there's always going to be to the third power down here. So if I put in 10,000, it seems like the top and the bottom would be the same, but the bottom is 10,000 to the third, so it's going to get huge. And when you think about a fraction, if the fraction, the denominator is huge compared to the numerator, then that value is getting very small. Does that make sense? It's approaching 0. When the bottom is a lot bigger than the top, the value of the fraction gets very tiny. All right. When the functions have equal weight, so we have a degree 2 over a degree 2, okay? Then what happens is it says the asymptote will be y equals c, where c is the ratio of the leading coefficient of the numerator over the denominator, or y equals leading coefficient over leading coefficient when they are equal weight, okay? This is for this one, equal weight. So for this one, we had a leading coefficient of 1. This one had a leading coefficient of 2. So we would get y equals 1/2, and that would be our horizontal asymptote. Now, the third possibility is that it is top-heavy. So for top-heavy, let me do that one in blue here. If you had an x cubed plus 2x minus 3 over an x minus 1, that's top-heavy, okay? But in Algebra 2, you may have learned that top-heavy meant it had no horizontal asymptote. Well, it doesn't, but instead it has either a slant asymptote or some kind of other end behavior equation that's nonlinear. Now, I'm going to go back and change this question a little bit. If I change the top to an x squared here, it's still top-heavy. It is 1 degree heavier. So therefore, what you have to do, it says, is the quotient. Quotient means we divide. And on this one, we could do synthetic division. 1 times 1 is 1, 2 plus 1 is 3, 1 times 3 is 3. Oh my gosh, it came out even. Well, that's not good. It actually means there's a hole there instead. All right, I'm going to change this to an 8 on the back. So it came out with a remainder. But the bottom line is you get to throw away the remainder. It says the quotient is the slant asymptote is the quotient of p of x divided by q of x. And it should say ignoring the remainder. You get to ignore the remainder here too. So when we divided this out right here, we would get y equals x plus 3 as the slant asymptote. And finally, if they do not differ by 1, if this had been an x cubed over an x, you would divide it out, and what you would get is an x squared, and we'll talk about that in a second. Oh, hit the second's up. Here we go. When you have something like this, x cubed over x minus 1. If you do synthetic division, this is 1x cubed plus 0x squared plus 0x plus 0. So if I do synthetic division to see this is top heavy, because it is a degree 3 over degree 1, When I bring this down, multiply, add, multiply, add, multiply, add, okay? You get to throw the remainder away, gone. What's left here is a 1x squared plus 1x plus 1, which is a parabola. That means the end behavior of this polynomial, whoa, there we go, x cubed over x minus 1 will actually look like a parabola. If we zoom out far enough, now it has two pieces on either side of the line x equals 1. So here is a vertical asymptote at x equals 1. But the piece over here is doing this, and the piece over here is doing this. And if you zoom out far enough, it looks like this is just a parabola that had a glitch. Okay? So that's why it can have an asymptote that's nonlinear. We'll practice that tomorrow some more. All right. Now, finally, the x-intercepts, well, think about this. If you have a fraction, when is it going to equal 0? A fraction will equal 0 when the top is equal to 0. So the x-intercepts are when the top equals 0. As long as it doesn't also make the denominator 0. The y-intercept is always when x equals 0. So you just plug in 0 and you see what you get out. All right. So here's our first example, and I'm just going to talk you through this one. It says determine any asymptotes and x-intercepts for this function. All right. The domain cannot equal 3 because the denominator cannot equal negative 3. The domain is all real numbers except negative 3 because that would make the denominator 0. So here's the domain. X cannot equal negative 3. Then there is also then a vertical asymptote at x equals negative 3, which is right here. This graph has counting by 2's, okay? X equals negative 3. And when you write an asymptote, it has to be an equation. You can't just write negative 3. You have to say x equals negative 3 so that it's a line. Then if we go back here, this particular equation was a degree 2 over a degree 1. Therefore, it is equal, just kidding. Oh, it is equal weight because this is an x to the 1 over an x to the 1. So let me write that so that you're not confused. So it's degree 1 over degree 1. So it is equal weight, which means the rule is you do y equals leading coefficient over leading coefficient. And that's where the 2 comes in. This 2 is a leading coefficient of 2. Down here we have a leading coefficient of 1. So we get y equals 2 as the end behavior or horizontal asymptote. So that is this line because they're counting by 2's. So that is the horizontal asymptote. All right, then we want to finish graphing it. So we look for some key points. If you plug in a 0 here, you get negative 1 over 3. So 0, negative 1/3. Because, guys, when this is 0, that's all that's left is negative 1/3. All right, then finally, the x-intercept is when the top is equal to 0. So that would be 2x minus 1 equals 0, x equals 1/2. So it is crossing the x-axis at 1/2, negative 1/3 on the y-axis, 2 asymptotes, and then after that, you can type it in your calculator to graph it. But to do that, you have to be real careful and put parentheses around the top. You would go y equals 2x minus 1 parenthesis divided by parenthesis x plus 3. Both the numerator and denominator have to be in parentheses. And then it would show you, and you could look for some extra ordered pairs to make a nice graph. All right, this is an extra example. I'm just going to run through real fast. You don't have this one, I don't think, but the domain is x cannot equal 3. That means there is a vertical asymptote at x equals 3. And can I bring this up here? Okay. They have graphed it with x equals 3. There is a 0 when the top is 0, so -4 would make that a 0 on top divided by something, but it would come out 0. And there is a y-intercept when you plug in a 0, so you would get 4 over -3. So it crosses the y down here at -4/3, which is between 0 and -2, okay? Because they're counting by 2s. It crosses the x out here at -4. It has an horizontal asymptote. It is degree 1 over degree 1, so it's equal weight. So it's y equals leading coefficient over leading coefficient, and both these leading coefficients are 1. So y equals 1 is where this horizontal asymptote wound up. Okay, so that was an extra example. You have this one. All right, we're not going to look at this yet. We're just going to talk about the features of this graph. So the first thing we need to do is figure out the domain, and to do that we need to factor the denominator because there's an x squared in the denominator, which means that we have 2 vertical asymptotes. All right, x equals 0 is a restriction on the domain, and x cannot equal 6 is also a domain restriction. So therefore, there are vertical asymptotes at x equals 0 and x equals 6. I know it seems confusing. You just said they can't equal that, so why are there vertical asymptotes? That's because the vertical asymptotes are boundaries. They're not actually part of the graph, but the equation for the line that is acting as a boundary is x equals 0 and x equals 6. All right, then we can talk about the top would equal 0 at -2. So that is a vertical, or I'm sorry, that is an x-intercept. We can talk about putting in a 0, but if you plug in a 0 back here, you get 2 over 0. And that's because, remember, the y-axis was asymptote, so it's undefined. So it has no y-intercept. Okay, I think all we're missing is the horizontal end behavior. And the degree 1 on top, degree 2 on the bottom, because it had a squared. So that means it is bottom heavy. And the rule for bottom heavy is y equals 0. Again, if I put a 10 in here, just think about this. I'd get 12 over 100 minus 60 would be 40. So 12 over 40 would reduce to 3/10. It's getting very, very small. The bigger number you get, the smaller the fraction is getting. So it is approaching y equals 0. Now, so what's going to end up happening is we're going to type it in our calculator and it's going to approach 0 over here. But I got to tell you, this particular one, I believe, crosses here. All right, when you type this in your calculator, you really should type in the unfactored version, which was x plus 2, all in parentheses, and then divided by the quantity x squared minus 6x. So is that right? Oops, I got two minuses. All right, and then you could try a zoom 6. Now, this looks like it stops here, and it looks like it stops here. It doesn't actually stop. It's because there's no room for it to show you that it's going almost vertically. It's very confusing if this is all you graph, okay? You have to know those features that we talked about. Now, the other option is sometimes a zoom decimal. We'll show it a little bit better. It still looks like it stops, and you actually don't see this piece over here, but it doesn't stop, okay? As you get closer and closer to x equals 0, the y gets bigger or smaller, depending which side of the axis you're on. Let me show you one more thing. The other thing is if you go to the table and you see that out past -2, the y values are actually negative. Okay, it did cross that asymptote, but they are getting smaller and smaller. They stay very, very, very close to the x-axis. So, where's my cursor? Here we go. It comes down here, crosses, and stays really, really, really close. Okay? Can cross a horizontal asymptote. Now, what's happening between here and here? Anytime you have a vertical asymptote, something happens on either side of it. Okay? So this graph has to have 3 pieces because we had 2 vertical asymptotes. This one was very easy to see, but sometimes that little piece in between there is off the top or off the bottom of your graph, so watch for it. This one, we wanted to know what's happening for some positive numbers here. 1 is -0.6, 2 is -0.5. I don't think we're getting anywhere. 1 is -0.6, 2, oh, that's 2 anyway, -0.5. All right, it's very flat in here and does this. All right, I am not grading on accuracy of your graph other than those features and maybe a couple ordered pairs if you can find them. But the features mean you need the x and y intercepts to be accurate and all that stuff. All right, so here's a little slide that says when there's 2 vertical asymptotes, it means there's 3 separate pieces of the graph, so look for them. Here's a little slide that says you always need to find the domain, sketch the asymptotes, find the intercepts, and then it says you can test intervals to see what it's doing, but I'm going to let you just graph it on your calculator. That's what we got them for. All right, quick 3 questions on the top of the back. It says, find the domain of each function and the equations of the vertical or horizontal asymptotes. Okay, x squared plus 1. If we set that equal to 0, that has imaginary numbers. You square any number, it becomes positive. You add 1, it's still positive. This is never going to be 0. So it has no vertical asymptotes. It is bottom heavy. The top is degree 0. There's no x's over degree 2. So the horizontal asymptote is y equals 0. And actually the domain is all real numbers because this never equaled 0. All right, this one. Can we factor that 2 out of the top? The answer is no. If we set the top equal to 0, we'd get -1/2. But x cannot equal -1. There's our domain. It's all real numbers, except x cannot equal -1. If you just write x cannot equal -1, I'll count it. It's fine. The vertical asymptote, therefore, is at x equals -1. And the horizontal asymptote, well, again, this one is degree 1 over degree 1, so it's equal weight. So that means we have y equals leading coefficient of 2 over leading coefficient of 1, or just y equals 2 for our horizontal asymptote. And this last one, it's easy to tell the domain restrictions. X cannot equal -1 or 2. So there are vertical asymptotes at x equals -1 and x equals 2. But because it's already factored, we have to be thinking a little bit. If we FOILed the top, the top is degree 1. But if we FOILed that bottom together, and you really don't have to, but you'd get x squared minus x minus 2, it is a degree 2. You should notice that because it has an x times an x, so it's degree 2. So therefore it's bottom heavy, so it approaches y equals 0 as the horizontal asymptote. All right. Now, the slant asymptote, I feel like we already talked about that. These, this is just vocabulary. I keep saying end behavior asymptote because when you have a slant asymptote, it's also called an oblique asymptote. Okay, I don't think you have this slide, but oblique and slant asymptotes are ones like this. We're going to have one here in a minute. We have a vertical asymptote and a slant asymptote. You might have a piece of the graph up here and a piece down here. And there's also the idea that it could be nonlinear. It could be a parabola, and we'll do some more of those tomorrow. But what's happening is these ideas are all called end behavior asymptotes because it means far out on the sides, what is it approaching? So it's called an end behavior quadratic asymptote, this one is. Okay. Find the domain for each function. Oh, this is an extra example you don't have. Just going to show real fast if you know what? I think I'm just going to do this one in the notes and not in the video. Okay, so check out the notes or try this one on your own. I'm going to move on so the video is not so long because we still need to talk about holes. A function has a hole if there is a factor of the numerator that is the same as a factor of the denominator. So I had x minus 2 over x plus 5, we'll say, and down here I had an x minus 2 and an x plus 3. This has a hole because there is a common factor here. You would cancel this out, but only after saying x cannot equal 2, or in my case, -3, for the domain. But when you cancel it, okay, you now say x equals 2 is where the hole is, and then you plug the 2 back into this reduced version of the function. So 2 plus 5 would be 7, 2 plus 3 down here would be 5, and you'd have a hole at 2 7/5. Okay, I just made up that example. But the idea is the hole, this is canceled out, but you need, before you cancel it, you need two things. You need to state it's a domain restriction, and you need to tell me the x of the hole, and then plug it back in. What you need to not do, there is not a vertical asymptote at x equals 2. If there's a hole, there's not an asymptote. If there's an asymptote, there's not a hole. It's one or the other. All right, this is called a removable discontinuity. Here's an extra example that you don't have. They factored the top and got x minus 2, x plus 2. They factored the bottom and it factored x minus 4, x plus 2. So there was a hole here. So you would say the domain is x cannot equal 4 or -2. Then you'd go ahead and say there's a hole at -2. And to find the rest of the hole, I cancel that out and I plug a -2 back in. -2 minus 2 over -2 minus 4 would be -4 over -6, or positive 2/3. Okay, that's how you find the hole. You plug it back in, the reduced fraction. The reduced fraction. So you have this reference sheet. I referred to it yesterday. It says it's easiest to find the y-intercept before you do anything else. Then you factor the top and bottom. The domain is all real numbers except those that make the denominator 0. Make sure you don't cancel anything out before you find the domain. Then if there happens to be a factor top and bottom, there is a hole. to find the ordered pair, you put the x value into the reduced rational function. You cancel the whole out. Anything left as a factor of the denominator, in other words, it's the factor of the denominator but not the numerator, that's when you have a vertical asymptote, and it can't be both a whole and a vertical asymptote. And then you have zeros or x-intercepts when the top is equal to 0. And the degree, okay, if it's bottom heavy, it approaches y equals 0. If it's equal weight, it approaches leading coefficient over leading coefficient. And if it's top heavy, then you have to divide, okay? It could have a slant asymptote or an end behavior equation. To find either one, you divide and ignore the remainder, okay? Remember, when it's an asymptote, it has an equation. It's either x equals for vertical lines or y equals for any kind of horizontal or end behavior function. And there's an example at the bottom. They factored this -2, remember, did nothing, okay? It stretched the graph, it made it the shape it was, but there was a hole here at x equals 4, not a vertical asymptote, and then they canceled that, so they were left with -2 over, I'm sorry, yes, they canceled that, and they put the 4 in here. 4 minus 2 is 2. Oh, so this is -2 over 2, sorry, which is -1. So the whole turned out to be 4, -1. All right, you have that example on your reference sheet. We're going to do 2 more questions. We're going to factor the top, but before we do anything, we're going to put in a 0. You put in a 0, this goes away, 3 times 0 is 0, this is 0, this is 0, so you end up with 2/4. So when I plugged in a 0, I got 2 over 4, or 1/2. That is the y-intercept. I always find that before I do anything because it's easiest to plug it in right there. Now I'm going to factor. The top factors x plus 2, x plus 1 to give us a 3x in the middle. Factor very carefully. The bottom factors x plus 4, x plus 1. All right, so before you do anything else, the domain restrictions are x cannot equal -4 or -1. The next thing you're supposed to look for is a hole, and there is a hole. There's a hole. Okay, I can't write. There is a hole when x equals -1. Then we're going to cancel that, and we're going to find the actual ordered pair of the hole by plugging -1 in here. So -1 plus 2 over -1 plus 4 would be 1/3. So the hole is at -1 and up 1/3. Make a nice big hole on your graph so I can see it. All right, that leaves us with a vertical asymptote down here, what makes the denominator 0. So there's a vertical asymptote at x equals -4 over here. The x-intercept is when you set the numerator equal to 0. So x plus 2 equals 0 would mean -2 is a 0 right here. The y-intercept was 0, 1/2, which would be right here. All right, so then I have all my features. I just have to figure out what it looks like. So I typed it in. Always type in the unfactored version, because then you'll notice if something is wrong with how you factored, and you won't need so many parentheses. If you factor and then put it in your calculator, you would need an extra set around the whole top and an extra set around the whole bottom. And you want to type in the original one. Okay, so I typed this original one in. This is what I got. Okay. And I did check. I put in a -1. And it came up undefined over here. Do you see this? There's nothing there. It's very hard to see the hole on this window because of the pixels, but -1 has no value. So I actually did a zoom decimal and then it showed up. The whole showed up right here. All right. Yeah. Finally, what you do is you go to the table of values. I'm going to pause the video and type this in, and then I'm going to go to the table and show you that real quick. All right, so I typed this into the, oh, I forgot the divide. Okay, I'm going to go back here, and I'm going to do second delete, which is insert, divide. There we go. Now it's got the divide in there. Then I am going to, I can do just a zoom standard. That's what it looked like. I did a zoom decimal, which is 4, and it showed the whole a little better. But I really want to plot a couple points, so I can either trace along or I can go to the table. The table helps me see that at -3, it's at -1. At -2, I already have that one. -5, it's at 3. So I can plot a few ordered pairs. Stick that right over here for a second. I can erase it in a minute. But I have -6, it's at 2. -5, it's at 3. Oh, where was the horizontal asymptote? Did we do the horizontal asymptote? Wow, I did not. It was degree 2 over degree 2, which is equal weight. So it is y equals leading coefficient over leading coefficient, both of which were just 1s. So y equals 1 is the horizontal asymptote right here. Okay, which explains why the graph is doing this over here. And then it's down here touching these spots. And if I put this back up here, at -3, it's down at -1. So it's bending this way. And as we go out this way, it gets closer and closer to 1. Notice it's getting 0.75, etc. Okay, so use that table, which is second graph, to find values and plot them, so that you can make it fairly accurate. All right, last one. This one is top heavy. Okay, so first thing I'm going to do is plug in a 0 to find the y-intercept. This would be 0, this would be 0, this would be 0. I have -6 over 1. So the y-intercept is right down here at -6. Should have made bigger graph paper for this one. Okay, then I factor the top, x plus 3, x minus 2. And I look at the domain restriction. X cannot equal -1. That is not a factor of the top, so there is a vertical asymptote instead of a hole at x equals -1. The last one had a vertical asymptote and a hole. All right, then there are 2 zeros that make the top. The x-intercepts are things that make the numerator 0. So I'd have -3, 0, and +2, 0. 1, 2, -1, -2, -3, +2. All right. Y-intercept, x-intercept, domain restriction. Okay, I am left with the end behavior. So I have to look at the degree. It is degree 2 divided by degree 1. This is the only example today of a top-heavy one that I'm doing with you. When it is top-heavy, you have to divide and ignore the remainder. Because this is an x plus 1, we are allowed to do synthetic division, because remember, you can do synthetic division as long as it's x minus or plus something. Okay, and this was just an x plus 1, so we put the 0, which is -1. What would make it 0 goes in the box. Then we put our coefficients across the top. It was a 1x squared plus 1x minus 6. We bring down the 1, we multiply by -1, we add and get 0, we multiply by -1 is still 0, we add and get -6, but this is the remainder, and the remainder gets thrown away. So this equation was just y equals 1x plus 0. So our end behavior equation is a slant asymptote or oblique asymptote at y equals x, or 1x plus 0. It goes like this. I'm going to make it a dotted line because it is not actually part of the graph. All right, so then I'm thinking, look, we're over here. We had a y-intercept, remember, way down here. So the graph, when I graph it on the calculator, I typed it in just like this with a whole bunch of parentheses, or parentheses around the top and the bottom. Unfactored version, and this is what it looked like. I'm not going to take time to find a bunch of ordered pairs because they're not going to be nice anyway. But this is the shape. It was crossing way down here. Whoa. Should be curving. All right. So this one had a slant asymptote. All right. I'm going to go back and do that one example and post the notes with all of this done. Oh, here's an extra example too. I can talk through this one as well, or you can look through this one. It'll be in the slides. Okay.